If you guys, well, I guess we'll get started now. It's 1:15, so this is probably about all the people are going to show up. But let me tell you what's going to go on in this tutorial. Actually, let me pull up the talk first. I wasn't sure exactly what kind of computational facilities I would have when I show up to the site. In fact, I've taught computational talks in scientific programming a couple of times, like in these little workshop type of things. And every single venue I go to is a little bit different. So I constructed, assuming minimum resources, of which we actually have more here than I expected, but assuming minimum resources, pretty much everything that I'm going to talk about is up on the slides, and I wasn't sure whether or not people would bring laptops or not. Another issue with getting any kind of scientific programming tutorial up and running is making sure that everybody has everything installed properly, which usually ends up taking about a day to do, and we don't have a day. So I wrote the talk basically so that you would have all the slides, all of the little R scripts that I wrote for the talk, so that you could try to reproduce some of this stuff yourself. And well, I'm going to be here probably until Wednesday, so if you do see me in the lecture at any point and you try to get stuff up and running yourself, it's just not working, I'm happy to help you at any point. But especially looking around the room, I don't see any laptops, so it's not going to be very interactive, so it's going to be watching me do this. But you should be able to reproduce all of this stuff yourself. If you did bring a laptop with you, which it doesn't look like anybody, but if you did, everything that I am going to talk about, I put on this little memory stick. So feel free to have it. Let me just show you before I get into the talk what's on there. So when you open up this folder, it's not like gibberish that you're looking at. So inside this folder, you will find it'll say SurfMet 12. Because this conference used to be called Surface Metrology. So in that folder, there's a couple other folders. There's a data folder for little example data that you can play around with. In the folder called R, that's where I have a lot of the R scripts that you need in order to slice and dice the data a little bit. And they're written such that this is actually what my group uses for research. When we want to work with surface files that we have from some kind of 3D microscopy, after we've done usually some kind of pre-processing with Mountains Map, although we're trying to get away from that, but once we've done some pre-processing with Mountains Map and we have something stored in a Mountains format, then we open it up into R, and then we can slice and dice it however we want. If you have experience with MATLAB, R is very, very similar to MATLAB. In fact, I think it's much more advantageous for surface metrology, especially if you want to get into statistical analysis and data mining and doing different things with your surfaces, because R is considered the standard in computational statistics to implement new methods. So if a new method or a tried and true method that a lot of people use is around, there's an R package around to do it, to execute it. And you don't have to reinvent the wheel yourself. A lot of the problems with any kind of scientific computing research is the amount of time that you have to invest in programming things. R makes it a little bit easier because a lot of people are working on R, much more so for data mining and data analysis type of things than in MATLAB. So if there's something new that you want to do, R probably has a package. Also, it's a full scripting language, so if you have an idea for a new parameter that you want to try out, just implement it in here, and the code is very similar. We'll talk about what the code looks like, and we'll go through the syntax. It looks very similar to MATLAB type of thing. There's also a lot of books around, too. And also, because I can only take one of these talks, I'm a professor, and so I'm used to watching people go, and I know myself, I can only take about an hour and a half a lecture at a time. We'll go for about an hour and a half, we'll take a break, and then we'll do the second half of the lecture. If I start getting kind of crazy, just warn me when we're getting close to an hour and a half, and then we'll take a break. Yep.
A question, you mentioned that you use Mountains to do some pre-processing. Mm-hmm. Are you going to go through what is important about that pre-processing?
I wasn't going to, but I could talk about what we do. I wasn't going to, but when I get up to the pictures where we actually see the tool marks themselves, I'll talk about exactly how we got them. Okay. But I wasn't going to do that.
I'd like to understand, if there's certain features like that you can't do with an R easily. that you're doing?
Yes, that I will talk about, absolutely.
I'd like to know what...
In fact, that's kind of why we have relied on mountains for the last 2.5 years or so, because like for filtering type of things, if you want, it's definitely that stuff's around in R, but not in as nice and easy to use a form as mountains. Mountains is really, I mean, don't get me wrong, mountains is great, and in terms of workflow, it really makes life so simple. But if there's anything fancier that you want to do that's not in mountains and you don't want to wait around for it to be implemented, or chances are it's never going to be implemented, they're not going to put neural nets or fancy kind of neural nets into mountains math because 5 people in the world will be interested in using them. That's what this talk is about. If you have pre-processed things in mountains, and believe me, mountains can do a lot, especially the things that surface metrologists are really interested in doing all the time in standard ways like filtering. Use mountains first, but then once you have done whatever you want to do to your surface as easily as you can do it in mountains, you want to do something new, this is how you dump it out of mountains into this particular program. Although when we first started doing this research, mountains didn't have the add-on for MATLAB, so I couldn't talk to MATLAB directly from mountains, but now apparently you can. I would still say I would go with this personally, because there's so many more data mining techniques implemented for R than there are, and data analysis techniques implemented for R than there are for MATLAB. And for the foreseeable future, I think that's going to be the way it is. All right, so what's in here is, so you're going to have some data. Within that data set, I'll tell you what's in there. What we did is we scanned tool marks. We do it with 3D confocal microscopy, which I'll talk about in the talk. But you could do it with any kind of microscopy you want. If you could dump out a bunch of surface parameters, you could dump them into a spreadsheet file. You can easily take that spreadsheet file and put it into your analysis in R. So that's what this is. We took just a bunch of the surfaces that we have and we put them into an Excel spreadsheet. So I'm going to show you how to load, like if you have something like an Excel spreadsheet, how do you load that into the program? Also, I have a bunch of example surface files that we've used for research in mountains format. These were originally recorded with a Zeiss CSM 700 white light surface scanning confocal microscope. We opened them up in mountains. We did our pre-processing, which is basically form removal and waviness, roughness separation. And then I save them in this format. If it has a _A on it, that means everything. All I've done here is form removal. If it has a W on it, that means it's a waviness component. And I'll talk about the filters that we use in order to get there. If you want something fancy like a wavelet filter, and you don't have the newer versions of mountains, you can do all of that stuff in R. The nice thing about R is it has full support for wavelet analysis, 1, 2, and 3D stuff. In fact, there are a couple of packages for it. You will have to do a lot more on your own. In other words, you have to do some of the nuts and bolts. You have to be more interested in putting the nuts and bolts together yourself. It's not the kind of thing you can just push a button and it'll filter for you. So you have to choose basis. You might have to, play around with exactly what the format of everything that goes into the filter looks like. But we'll talk about that as we go. That's something actually that's still kind of research level for us in my group that we're just getting into now, wavelet analysis. Anyway, so you have a couple of practice surfaces that were originally recorded with the Zeiss, but we saved in mountains format. The really nice thing about mountains format that I appreciate a lot is that they published the format of that file. So I know, like, if we go to a particular byte in the header, I know what that's supposed to represent. We read it right out, and I'll show you, and you can have that code in R if you'd like it, and open up your stuff. So you have parameters and a couple of surfaces. This is the data that you can play around with. You'll also have the talk and all the slides that are in the talk, so if you'd like to play with it, please, some of it is unpublished material. Please don't publish it and put your name on it, although if this appears in print, you expect to get a letter from me and several other people. I don't mind. I really like collaborating. I get a lot out of collaborating with people. Yeah, there is some unpublished stuff in there, so please don't just have your name on it and say, hey, look at what I just did. But I've never had a problem before, so I don't mind giving it to people. And my philosophy, too, is that science does not progress if you keep everything to yourself. If you're the only group in the world that can do this particular technique, it's useless to people. I've come across that a number of times where, oh boy, I would love to be able to do that calculation, and it's only going to take me 5 or 6 years to figure out how to reprogram the whole thing. So, I don't like reinventing the wheel if I don't have to, and I try to practice that philosophy with my science as well. Within this little thing that you'll be able to, did I start? Oh, I didn't pass it around. Sorry. Yeah, it's coming around, you can load it on. within that folder also, there'll be a couple of R scripts, and we'll talk about using them and what they can do. Pretty much everything that you see that's a picture of a graph or a bunch of points in space that are maybe 3 dimensions, you can reproduce with these scripts. I have mostly geared them to work with the parameters file, not the surface files. It's not that much more work to get them to work with the surface files, but again, because I didn't know exactly what the level of the audience would be or how much computational facility I had, mostly it's a lot slower with the surface files, because each surface file has about 7, I just checked, it's about 7 million points or so in there. So it can be a little slow. If you want blazing speed, don't use R. Don't use MATLAB. Hire somebody and hard code everything in C. If speed is what you're looking for, this is not really for you. If you're looking to do research because you don't really know how to handle your surfaces, or you have a new parameter or a new filter you want to implement, or some other kind of crazy research that you want to do, this is probably a little bit more along the lines for you. But it's a nuts and bolts kind of thing. It's not GUI driven. So let's talk about it. I'll give you an introduction of who I am and what we're going to speak about today. So I'm going to go kind of slow. If we get through everything, great. If you don't, that's no big deal. Really, the goal of this is to be able to get you guys to load data into R, whether it be a parameter, a Excel spreadsheet full of parameters, or a surface that you've saved in Mountains format. And again, I picked Mountains format because that format is published. And pretty much Mountains can open up any surface file out there, so you can always save it in Mountains format and then open it up into R if you'd like. And I'm sure, like most of the microscope companies I've ever talked to, if you want their format there, just as long as you don't go and like make a commercial product with it, they're happy to give it to you. I just picked this because I figured it would be fairly ubiquitous. So my name is Nicholas Petraco. I am a professor at John Jay College of Criminal Justice. My background is actually quantum chemistry, although I've never really been very much of a quantum chemist. I've always been more of an applied mathematician. I never did very much chemistry. I always did computing. And when I got the job at John Jay, needless to say, were not interested in quantum chemistry very much because there are forensic scientists there. It's a school originally started for cops and firefighters in the 60s. It has since evolved into other things, but still the major programs there are criminal justice, forensic science, and forensic psychology. And I work with the forensic scientists. And one thing that I could do that not a lot of forensic scientists can do is I know how to program a computer. So I started switching my interest from quantum chemistry into data, instead of looking at chemical data, but looking instead at data that's of interest to the forensic scientists. And one thing that I really was interested in, because I'm a little bit of a closet gun nut, and I work with a lot of gun nuts as well. I got into firearms and tool mark analysis, and that's really a great field for surface metrology. It really fits very well into it. So I'll talk about a little bit why we're interested in that from a forensic point of view and the problems that are going on with the court, and just how we began to approach the problem such that all of you should be able to, with enough work, be able to reproduce what I talk about today. And feel free, because this is a tutorial, it's not a research talk, interrupt me with questions at any point and ask anything you would like. So I'll talk a little bit about forensic science interest in surface metrology. Why is a quantum chemist who's changed into a forensic scientist interested in engineering at all? And then I'll talk about R as a potential platform for computational surface metrology and statistical analysis. Not to beat up on anything else, but I'm going to tell you about why we have felt it to be so useful. If you're really into MATLAB, or if you really like to hardwire things in C, great. In fact, I'd love some of your code. At any rate, I'll talk a little bit about R and getting used to it, and then how to pull data into it. Then I'll talk about, once you have data in there, how to visualize some different ways that we have used to visualize that data. Because one of the important things, although this is anathema to a lot of statisticians, is I like to look at my data. I don't really like to make lots of decisions about how I'm going to analyze that data until I see a couple of samples first. I'm just the kind of person who needs to visualize things. Statistics, you're not really supposed to do that. You're supposed to come up with your analysis first and then do your, then look at your data. Well, I always look at a little bit of data first. So, you know, along the lines of John Tukey, I like to sort of think about what my data is trying to tell me before I go bananas with lots of different kinds of analysis. Then I'll get new data sets. So I'll talk about some of the things that we do there. I was originally going to do a lot of different kinds of techniques, but I gave a version of this talk last year, and we got through like one. So I decided to cut out one or two. I'm going to talk about what we have found to be the most effective for surfaces. That is principal component analysis, which is actually already implemented in. It's really simple to implement it. It's in mountains already. It's called Coulomb-Love transformation in mountains. One of the names for PCA is I believe they're German guys in the turn of the century came up with exactly the same method called Coulomb-Love transformation. That's PCA. You could do it in pretty much any kind of software that's out there. I'll tell you how to do it in R. And then I'll also talk about something that works a lot like neural nets, except a little bit easier to use, called support vector machines. If you have a bunch of data, how do you make decisions about groups in that data? In other words, if you have an unknown, which group do you think it best belongs with? One way to do it is neural nets. There's a zillion and one different other ways to do it. You name it, there's an R package for it. I'll talk about the support vector machine way of doing this, because it's a little bit easier to use in a neural net. For forensic, and this is sort of the more pie in the sky type of stuff, the research level that I don't think we'll get to, but once you've built a model of your data and decided how to make decisions about unknowns for that data set, really in forensic science it's very important to gauge how often you actually might be getting the right answer. And this is a real big bone of contention in the field right now. If we get to it, I'll talk a little bit about how do you estimate error rates once you've trained your model up, and how do you test it, and different ways of doing that, and putting levels of confidence and maybe even probabilities of random matches on those things. This is a little bit more, not so necessary for engineers, but very necessary in forensic science. So if we get to it, we get to it. So just before we get into the tutorial section of the talk, this is what's going on in forensic science right now. In 1993, a Supreme Court decided the famous Daubert v. Merrill Dow Pharmaceuticals case, where the Supreme Court basically made judges gatekeepers of what is scientific in the courtroom. Until that point, the way whatever was proffered as scientific in the court, the judge would decide whether or not there was enough evidence that that technique was generally accepted by the community from which it comes. So that's really wishy-washy. There's a lot of things in the law that are really wishy-washy, but that was particularly wishy-washy, and that was called the Frye standard. New York State, where I come from, is still a Frye state. So if you are under federal prosecution under state law in New York State, and you come up with some crazy scientific technique that proves that you're innocent, it'll be subject to a Frye test. Is it generally accepted by whatever scientific community from which it comes? If you commit, I think Massachusetts is a Daubert state, or Daubert-like state. If you commit a crime here and you have some crazy scientific method that you come up with, you'll undergo a Daubert hearing. Also, federal government is a Daubert jurisdiction. And in Daubert jurisdictions, which in all the United States is kind of trending towards this, standard, the judge has to decide, has empirical testing been done? In other words, is the scientific method falsifiable? Has it been subject to peer review? Are there error rates or known estimates of error rates for the particular method? And then finally, the fourth prong is the Frye standard. So the judge doesn't have to decide on all these, but they have to pick at least one, and the Frye standard is built into it. And the reason why I always put this up in front of any of my talks is because I do work with a lot of forensic scientists, and this is kind of how I was trained to be a scientist. Regardless of whether or not this is a right decision or a wrong decision by the Supreme Court, if I look at this list, this is what my boss, when I was a graduate student, told me to do when I was writing a scientific paper. Make sure you can test things and reproduce the data. If you want to keep your job, you better publish some papers. Especially for academia, peer review isn't that big a deal. We have to do it in order to get things like tenures and promotion and that kind of stuff. Computation of error rates is really the most fun for me because I'm a mathematician. I like to figure out new ways to compute things, or take accepted ways to compute things on different kinds of data and adapt them for my needs. So this is stuff that I do anyway, so it makes a good research area. So that's what I'll talk about. This is sort of where we're coming from with tool mark analysis. How do we make forensic tool mark analysis fit into this paradigm? In other words, how do we associate a weapon with the marks that it makes? And the way that this had been done in the past, and still continues to today, regardless of whether or not it's right or wrong, I'm not making any kind of value judgment, is somebody who's been trained in the field for a very long time will come to a qualitative assessment as to whether or not, say, marks on a bullet could have been produced by a particular gun, say the suspect's gun. We're interested in trying to take that surface data that exists on the gun, and especially on the bullets or the tools that you use in a crime, and make a quantitative decision about an association. So what kind of data can we use for tool marks? The data right away, it says, as soon as you're looking at something like a tool mark that says surface right away, surface engineers, surface metrologists have been studying this stuff for years. Let's try to use some of their techniques. Multivariate people have been trying to make decisions about data for years. Let's try to use some of their techniques. So let's take these two different fields, engineering and statistics, and see if we can put them together for our decision-making needs. That's sort of where we're coming from with this project. And just if you want a assessment of sort of who is the governing body of this, tools are transfer microscopic marks onto pressable surfaces, and these marks are made by the manufacturing use in corrosion, although if anybody in here is an engineer, I'm not telling you anything you already know. And the Association of Firearms and Tool Mark Examiners is a governing body in forensic science, which really sets the standards for tool mark examination as it's practiced today. And their statement that opinions of common origin can be made when unique surface contours of tool marks are in sufficient agreement is something that we in my research group are trying to quantify. How do we do that if we have a bunch of surface data? So from our point of view, taking as objective a stand as we can, all impressions made by tools and firearms can be just viewed as numerical patterns, and it's machine learning that's a set of techniques that trains a computer to recognize patterns. And they can yield identification error rates, and if you really want to go bananas, maybe we can even put on confidence identifications and posterior error rate probabilities, such that they will hold a lot of water to somebody who has a PhD in statistics or mathematics and says, okay, I can't see any holes in your method. If we get to this stuff, we get to it. If we don't, you have the slides, you can look at it. So data acquisition, the data that we're interested in, and I'm going to go through this real quick because it's not really too much part of the tutorial, but we use confocal 3D surface scanning confocal microscopy in order to scan tool marks. And we are scanning them and storing them in an ever-expanding database, because one of the things that we didn't quite realize about this research when we first started is any kind of 3D microscopy that you do is fairly slow. It takes a long time to get good data into the computer. Even if it's a fast confocal microscope, it's still kind of slow. It takes a long time to build up a database that you can make good decisions on. So we're recording them in an ever-expanding database, and also part of the grant that was funded to buy this instrument, we said we'd make the data available to everybody. So if you want, actually the data is available now on a website. Anybody want to see the website? I'll show you the website. You can sign up for the website and you can download the data to your heart's content. You just have to promise that you're not going to use it in any kind of court proceedings, because I don't feel it's ready, any of this stuff is really ready to go into court yet. And I also want to be relatively sure that whoever's using the data is using it in a professional way, and they're not advocating one side or the other. They're just trying to build better decision systems. If you want to go to the website, this is what the website does look like. It's at the very end of this talk. I have the URL for the website. We just got a new name, which sometimes works and sometimes doesn't. But this is what the website looks like when you go to it. Where did I put it? Let's see if it comes up. It did. I tested it before the talk, so let's see if this works. Oh, is it? Oh, yeah.
You've been redirected.
Yes, right. Nuts. Yeah, I got to sign into the website. When we take a break, I'll bring up the website and I'll have it up on the board for when you guys come back from the break, and you can see what it does. But if you want to download any of the Surface files, you can download them from that website. In a couple different formats: unfiltered, filtered, form removed, unform removed, whatever you want. They're just big files. So let me talk to you a little bit about some of the major data that's in that database. We have a lot of striation patterns, because those are the most straightforward thing to work with. And if we can't get the decision model right for something as straightforward as striation patterns, that a human tool mark examiner really does have an easy time calling a correct match and non-match. Oh, what?
I think it's not around.
Does anybody else need the stick? No? Okay. So if a human being can do this, we better be able to get a computer to do this. Then if we can't get a computer to even do this well, then we're really out of luck. So most of the data in there right now, although we're continuing to add data to the database constantly, are striation patterns. These are from screwdrivers and lead. These were recorded with the Zeiss. We wrote a little add-on to, because eventually I do want to get away from having to use mountains, mostly because it's just so incredibly expensive. But we wrote a little add-on in Java to a digital image processing program called ImageJ, which is a Java program which is written by the NIH. It's been around for a zillion years. It does a lot of nice things with microscopy. It hasn't really, although much to my surprise, hasn't been adapted very much for surface metrology. My group is one of the groups that are slowly adding to it to build it up so that it is actually useful to surface metrologists and perhaps even firearms examiners as well. And it should run on anything because it's written in Java. We wrote a little plugin for it so we can open up mountains files on it, and that's also available on the website if you want it. I didn't bring it with me today, but I do have it on, actually no, I have it on the computer, so if you want it and you know how to use ImageJ a little bit, you're more than welcome to it. And you can open up a mountains file on there, and it's, again, mountains beats it hands down. It's really a nice visualization program. But if you want to be able to open it up in 3 dimensions and move it around and interact with it a little bit, ImageJ is capable of doing that. So you can open them up in 3D and play around with it a little bit. We haven't corrected it such that it takes out these 16-bit Z values and makes them into actual physical values. So you just have to trust me that these are physical values, are just encoded in 16 bits. I haven't figured out how to do that yet. But if you can visualize things in mountains, do it. Although if you really want a rudimentary tool, you can also do it in ImageJ with our stuff. Something else that we have a lot of in that database are surfaces from Glock-fired cartridge cases. We have a lot of primer shears, which is most of the data that I'll talk about for this talk. We also have in there a couple of ejector marks, and we also have breech face impressions and bottoms of firing pin impressions. And one thing to note about almost any kind of 3D microscopy with light, it has trouble with steep edges. Sorry, Tom, ours has a lot of trouble yeah, I don't know of one that does not. We can get down to about, safely 50 degrees. Pretty much past 50 degrees, we start really having a hard time. So we just have bottoms of firing pin impressions because I cut it out. Around the rest of this is just a bunch of noise. And even if we filter out all that noise, I don't believe the data that's left over. I'm not sure that any of that is
Even
good.
if somebody says they can get to shear walls, ask them what they do about re-entrant surfaces.
Yeah, I've seen a lot of nice pictures in these research talks about these really steep 90 degrees. How the hell do you get that? I can't do that.
There are actually re-entrant surfaces in the fold of, things that fold over, and especially a large forming like that.
So there is, am I wrong? I mean, this is not my major field of expertise. Is there anything that can do that other than a stylus type of instrument? And then you'd need a crazy kind of XYZ stage.
The stylus, you're limited by the angle of the tip.
A hard time. The steep walls, where steep is in the eye of the beholder, are going to be a problem with most conventional optical systems by playing games with illumination and where the illumination comes from and things like that. You can get a little bit steeper.
Okay,
but not huge.
It's a hard problem to solve, I think.
Yeah, one way would be to use some type of replicate material and that fluoresces, and do it in fluorescence confocal microscopy, which then these side walls become emissive surfaces.
You have tons of photons there, and
so it improves it, but certainly at 90 degrees you have an issue.
Okay, yeah, maybe that's the way to go then. For it'll be interesting to see. I think I'd recommend everybody go to this gel site talk, because I think they're talking about stuff like that, trying to reproduce the surface such that I don't think what they have fluoresces, but it probably can be made to fluoresce, and then you can use fluorescent confocal microscopy on to get those really steep angles. Although I'll tell you right now, I know a lot of firearms and tool mark examiners, and they're gonna not like to work with it. But. So anyway, these kinds of surfaces are available, but this is mostly what we have in the database, these primer shears, because this is what we're most interested in getting. We had a sort of a limited time frame to get a bunch of data into the data set. now we're not under so much time constraint anymore, and we're sort of moved more into computational development stage that we don't have the money. The project has ended. We're started interested into these things as well, so we're starting to get into firing pin impressions as well, 2D marks. Yep.
What is a primer shear?
Good question. Good question. They're not on every. They're not on every kind of fired cartridge cases. Glocks are famous for them, though. If you ever look at I didn't bring a particularly great picture here, but if you ever look at a cartridge case and it has this kind of rectangular impression on it, it was probably fired out of a Glock. You need me? Oh, okay. Now, at the I have this rotated 180 degrees, so in reality, this came out of the gun rotated 180 degrees. What happens is the firing pin comes into the primer. The primer is very soft metal, so a lot of that soft primer metal gets pushed out, and the mechanism under which a lot of Glocks are designed is, I believe it's called the Browning mechanism, which basically ejects the cartridge from it. And in the process of that happening, the barrel drops down and it shears off a little bit of that primer metal, and it produces these nice, beautiful striation patterns, which, if they do appear on the cartridge case, the human beings love to line them up and make sure that there's enough agreement there that they can say this particular Glock fired this particular cartridge case that I found at the crime scene. We just want to make that more client. How do you get a computer to do that such that you don't say it's been my 30 years of experience? No, Judge, instead this is my recipe that I followed, and anybody can reproduce it if they have the same data set that I want. That's what the courts are asking for. Right or wrong, that's what they want. So how do you make a computer do that kind of thing? And they are over here, although just keep in mind, this is not the orientation that comes out of the firearm. It's the firearms guys get mad at me every time they see this picture, like, that's upside down. Yes, it is upside down. This is how we mount it on the scope, though, because it's a lot easier for us to deal with it up here than it is down here, just because of the way the stage works, and I can stick my head underneath the scope. I like to put it up here at 12 o'clock.
They can tell that it's upside down?
Yeah, they've been, a lot of them, I mean, it takes a long time to become a firearms examiner, so, and they look at tons and tons and tons of shells over the, like, bare minimum of 5 years of training that it takes to become a firearms. Yeah, they can tell. They look at this stuff and they know what they're looking at. But at any rate, that's where the primer shear is. And it's not on every kind of cartridge case. It's mostly the Glocks I put on. There's, I think, a couple Smith & Wesson models also that, although I should be careful they're recording this. Yeah, if the firearms guys see this and I make any mistakes, they're going to get really mad at me. But
you'll get a letter.
Yeah, I will. It's when I say a primer shear, I mostly mean I'm going after something on a Glock that was fired out of a Glock. So this is, once we've done a little bit of slicing of some of the noise that comes out on the edges, this is what the primer shears look like. And I usually like, whenever I talk to a bunch of lawyers as to whether or not, a lot of them are pretty hostile. My wife's a lawyer, so I'm allowed to say lawyers are hostile. A lot of the lawyers will get upset that, oh, how do you know that two different guns aren't going to produce exactly the same set of marks? I show them pictures like this and say, listen, they don't, once you really get to know this data and you really look at it, they're not. But how do we get a computer to reproduce what the firearms guys have been saying? And again, I'm not saying that that should be my conclusion. All I'm saying is, let's see if we come to the same conclusion looking at data that we can keep around in perpetuity and use the same kind of mathematics that are used to pair people with products. If you ever use Netflix or if you ever use Amazon, I'm using the same kind of algorithms to pair guns with the surfaces that could have produced them that Amazon is using to say, oh, well, you looked at X, Y, and Z, maybe you'll like this product as well. How do I make that computational association? If the toolmark guys are right, we should come up with pretty good error rates. If they're not right, well, good. The court needs to know that as well. So again, that's all kind of research level stuff. It's not tutorial.
So the causality, if you will, is that due to the manufacture of the firing pin, the surface of each gun has a different.
It depends on the manufacturer. Okay. And like some of the actual cheaper firearms, the manufacturing is such that things are a lot more similar than you'd really like them to be. Okay. Glocks are notorious for having manufacturers such that they really do look different from gun to gun to gun. For the cartridge cases, for the bullets, it's the opposite effect. But yes, that's the hypothesis, that due to the manufacturing, you're going to impart all these little different surface disparities such that no two tool marks are going to look exactly alike. On top of that, you also have use, and with use, everything changes. So, and I haven't yet to meet a person who commits a crime with a brand new tool. I mean, it's probably like usually crimes are committed like, oh, you know, my wife is mad at me or something like that, and I'm going to stab her. I'm going to go down to the toolbox in the basement with the screwdriver. I'm not going to go to Sears and buy a new set of screwdrivers and stab my wife. I'm going to go downstairs and get the screwdrivers that I have lying around already, and they have been used forever to open tin cans, to, you know, jimmy the jam door. You know, all sorts of things happen to. Tools have lots of history to them. Guns have lots of history to them. So it's not only manufacturing, but also use and abuse that imparts these unique features. We're just trying to make measurements and see if we can get a computer to match things up properly, like a human does. But we'll have a recipe. So that was all kind of boilerplate research stuff. It wasn't really too much tutorial. So let's get a little bit more into tutorial. We're making measurements on surfaces. That is, we're doing experiments. We're measuring random variables, and all measurements have some sort of associated randomness component with them. A lot of the lawyers that I talk to think, you know, kind of hold science on this pedestal, like if science tells you a conclusion, that's the conclusion. Well, there's a lot of randomness built into science as well, and there's a lot of subjectivity and qualitative reasoning built into science as well. There's a lot of randomness built into science as well. What people who don't usually do scientific or measurement techniques don't realize is that every time you make a measurement, you expect to get a slightly different answer. If you don't, probably something is wrong. And if you take a bunch of these measurements or random variables and you put them together into a list, just in case, I wasn't sure how, you know, if everybody would be familiar with the word vector. If you have a bunch of numbers, probably because it's an engineering audience, but if you have a bunch of numbers, you put it into a list, it's a vector. So we would have what we're measuring with surface metrology are random vectors, random lists of numbers, or lists of random numbers. That's what I wanted to say. It has a couple of different names. You can call it observation vector, or you can also call them feature vectors. These kinds of techniques are used in many different fields, and each one has its own lingo. I like to use the word feature vectors because I'm measuring features on surfaces, although ultimately what we're really measuring is a bunch of random numbers. Can I move on? Or if you don't have a laptop, so I see a lot of people taking notes, and because I'm used to this with my students. If you want to take notes, that's great, and I go too fast, feel free to tell me to slow down. Also, if your hand gets tired and you want the memory stick later, it's not my memory stick, so you can load it onto whatever you want and fish your laptop out later. I'm going to be around for the rest of the conference as well. So, and everything's on my laptop, so if you have a memory stick and a laptop and you want to stick it in here and put it onto your laptop, that's fine too. So don't worry if you don't get everything. And also, if I'm going too fast, I have plenty of material. Just tell me to slow down. Mostly today, I just want you to be able to get surface information into R so you can slice and dice it however you want. That's the major battle with this program. And by the way, I'm flattered that people are actually taking notes. I mean, you wouldn't believe how much I have to twist my students' arms to take notes. But at any rate, so potential feature vectors for surface metrology are as follows. We can measure entire surfaces and just transform that into a giant list of numbers. We could use surface profiles or slices of that surface. Look at that surface like a big loaf of bread and slice it up into a bunch of profiles. You could use Fourier transforms or wavelet coefficients. We're starting to get into wavelet analysis now. You can even use translation and rotation and scale invariant surface features that are used in digital image processing. Maybe that's the way to go as well. Mostly what we have been using at this point are surface profiles. We're starting to get into wavelet coefficients and maybe even some of these image invariant features as well from digital imaging, so that we don't have to do a lot of registration between the surfaces in order to make decisions about it. But neither here nor there. You could choose, at the bare minimum, any one of these sets of features to serve as a number characterizer for the particular surface of interest. So just so you have a little bit more in your head as to exactly the data that my group, is feeding into a program like R, and you can do this with MATLAB as well, is we're looking at striation patterns or scratch patterns, and we're taking mean profiles down those, mostly because that's what people in the literature have done so far. And if we were to use the entire surface, we have many megabytes of data to deal with, whereas if we use one of these things, we only have a couple kilobytes of data to play around with. And I think that's going to be the way it is until somebody really finds an effective discriminatory set of features that work for surfaces as well. You're not going to be, even if it's hard-coded in C or Fortran, you have so many megabytes of, even if you have 6 megabytes of information for one particular surface, if you have to look through thousands of surfaces in a database, the computer program is just going to take forever to run. So nobody's really solved that feature extraction problem yet. The way we kind of get around it at this point is we use striation patterns and we take mean profiles. There's only a couple kilobytes worth of data, so it's easy to deal with. And in fact, we filter it a little bit more, and we work with the waviness profiles. And usually we use a spline filter with a 0.02 millimeter cutoff or so to really pull out the lines that make up that striation pattern. If you look at the waviness profile in 3 dimensions, and you look at an actual picture of the striation pattern, they look like waviness patterns. Most of the essential information that's making it into the human being's eye, I could make a strong qualitative argument, is basically the waviness profile with the filters that we're using. Again, you can use as much or as little information as you want. If you think you could do this better than us, all the data is in the database, so you're more than welcome to it. Also, if you get your own confocal scope, you should be able to reproduce what we're doing as well. The R program that we have also will turn things into barcodes if you want. We haven't found those. At first we thought it would be very effective for discrimination. It turns out that there's so many peaks and valleys that when you start laying these barcodes over each other, you just saturate binary space, and we don't get very good discrimination anymore. At least that's the best example. That's the best explanation I can come with right now. This tends to work better for identifying the tool mark over this. And this is just not enough discriminatory information in there. But again, I don't know, this is still an open question. I'm not entirely sure which way we're going to go with that. So now that we have surface data, so everything I've talked about thus far is with you have some access to some kind of 3D optical or physical metrology instrument. And you can somehow boil that surface down into either a bunch of features or literally some kind of profile or mean profile. What can you do with that data once you have it? You can do a couple of different things. A lot of the microscopy, or a lot of the microscope instruments already come with a lot of software tools that you can play around with things, especially filtering. If you want to do anything fancier than that, you're probably going to have to either find a program that's external to whatever comes with the microscope or write it yourself. So if you want to write things yourself but not do a whole lot of work reinventing the wheel, we like to use the statistics program R. R is very easy to find on the internet. You type the letter R and it will, if you Google it, and it comes right up. Nothing dirty or anything like that, just R. If you want to get to it, if you want to actually install it on your computer, it runs on everything. So don't worry if you're a Mac user or a Unix user or a Windows user, it runs exactly the same way on all platforms, which is one of the powerful things about R. It is also free. In fact, it really isn't free because most of it was developed under NSF and NIH grants. So you've paid for this in your taxes already. It's open source, and you can open it, you can run it and look at the code and do whatever you want with it. And you actually, I say it's free, but it really isn't. You've paid for it in your taxes and a lot of graduate student, postdoc, slave labor has gone into it. And believe me, don't think that just because you pay for something, it is higher quality and something is free. One of the reasons why I like this is, believe me, if something doesn't work in this program, you'll see it in the mailing lists, which I think is, anytime police or lawyers bring it up to me that, oh, well, this is just open source, it's Wild West, anybody can do whatever they want to it. Enough nerds use this program. If it doesn't work, they complain, and you'll see it right away. And it's enshrined on the web, their complaints, forever. So if it doesn't work, you have user feedback someplace that says it doesn't work. And test it out yourself too. Don't ever use any of these programs black box. I mean, don't believe the results. See if you can break the program if you can. So it's maintained by a professional group of statisticians and computational scientists, mostly statisticians, although engineers, I think, are slowly beginning to realize that this stuff is out there. It has everything from very simple techniques from like t-tests and stuff you learn in Statistics 101, straight up through, you name the crazy data mining technique, there's probably an R package add-on that will do it. So it's sort of the standard to implement new techniques in. It has pretty good graphics, although I would say that the MATLAB graphics are a little bit better. But R definitely has very, very good graphics, and it's able to produce publication level graphs and three-dimensional plots. I still think MATLAB's probably a little bit nicer, but you don't have to pay for this at all, and it's always getting better. So. And it's fully extensible too. You can, it's a full scripting language, so you can write for loops, if statements. You can make whole big applications if you want. Although, again, if it really is big and you really need a lot of speed, I say reconsider writing it in something else. Although, if you do need particular routines to run very, very fast, you can write C functions for them and call them from R, just like you can write MX files for MATLAB and call them from MATLAB. So it works exactly the same way. Where to get this information? You could literally Google R, and it will come right up. The website is this, so that will be in your notes. When you go to the actual website, and I'll turn this on at the break, it's a little, when I first downloaded this program, I got a little confused as to what I needed and where. If you click around enough, eventually you'll see base. You want to click on base and just go into base. There's also a bunch, every time somebody writes a new R add-on package, that gets dumped into the contrib directory right underneath base. You do not need to go near that directory. It's just full of thousands of packages. You download packages as you learn about them and need them, and you can do that on the fly once you have the program already installed, and I'll show you how to do that. All you really need is the base. Once you click on base, it'll come right, your installer, which is just a wizard, will come right up, and it's really easy. Just go, 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 and it'll install for you on anything. Now, R itself is nice, and it comes with a little editor that you can type your code into, and especially if you use it on Macintosh, that editor has some color coding that's associated with it. One thing that I really like to do, or I got to be a lot better programmer when my code got colored for me, it's a lot easier to spot mistakes, and for whatever reason, my mind really responds well to colors. There is no color coding in the R editor for Windows, which is what most people use, and it looks ugly. It's just this gray level. It looks like when I was a graduate student, I had to use VI all the time. It's just this gray code. Luckily, people have been writing IDEs, or integrated development environments, for a while for R. There had never really been that great a one until this came out about 2 years ago, called RStudio. RStudio is a Java program which, once you have R installed, it plays wonderfully with R, and it color codes things really, really nicely. I'll show you a screenshot of it in just a second so you can navigate your way around it. It runs on everything because it's written in Java, and it's a very nice, comfortable environment in which to program in R or do data analysis in R. There are other IDEs that do different things better than this, but this is kind of all in one package, and it works. I really like it. It works very well for doing most of the stuff that you'd ever want to do in R. And even though the plots within RStudio come out small, you can always kick them out into a separate window and make them as big as you want. You can save all of those plots as PDF files, or and then put them into Word documents or whatever you want with them. So it works pretty well. I have noticed a performance slowdown when we use it. If we just use the regular R script editor to do our coding versus running everything through RStudio, I have noticed a slowdown. But again, if speed is what you need, don't use this program at all. Don't use MATLAB. Use something that's going to run really, really fast. So, but be aware you might have some slowdown, a little bit slowdown performance issues with this. It is, I mean, every about 6 months or so they come up with an update, and it's not a very old program. So I think those speed issues will be addressed in the future. But right now it does, sometimes for the heavier lifting, it does slow down a little. If you want a particular technique. I keep going back to neural nets because I think that's a word that a lot of people have heard of it, but they don't really know what it is. It's a statistical discrimination technique where you try to say, okay, I have a bunch of data, and I know it's separated into groups. I want to find a function that will separate them into groups for me such that when I have an unknown, depending on what side of the function it ends up on, I can identify it. So let's say you wanted to do neural networks for R, and you don't know how to do that. Google R neural networks, and a bunch of things will come up. Probably a bunch of links to this website, CRAN. CRAN stands for Comprehensive R Archive Network. That's where a lot of the packages are stored. Actually, it's not one central location. It's a bunch of servers that all mirror each other all over the world. If you download and install a new R package, you're probably downloading and installing it from one of the CRAN servers. If you want to see what's on the servers, you can go to that website. But usually when I want to find a particular package or something new that I want to do, and I don't know necessarily what the package name is, I'll do a little bit of web research. I'll say, okay, R neural networks, and see what comes up and what people like and what they don't like. Then I'll show you what the commands are in order to install those packages into the programming framework. In order to search CRAN, in other words, if you want to see kind of what's already available on CRAN without going directly into Google and having to sift through a lot of garbage, all the way on the left-hand side of the CRAN website, there's a little search, so you can click on that. I would have given you the web address for it, except the web address comes up exactly the same if you click on the search. So I don't know exactly how web pages work, but you don't get a new web address if you click on the search. It's all the way on the left-hand side. You can't miss it. This is what RStudio kind of looks like, and I brought it with me. If you're new to programming and you want to get started with programming in Surface Metrology, I kind of felt comfortable with it because a lot of this looks like quantum chemistry where I came from. It's just a bunch of linear algebra. An excellent book to get started with. It doesn't have super fancy stuff in it, but it really has great foundations in it, and it's written in MATLAB. Is this book, Computational Surface and Roundness Metrology, by some people at UNC Chapel Hill, very famous surface metrology group. Jay Raja is, I believe, the guy who runs it. This book is really magnificent thing to get started with because it gives you he tells you what you're they tell you what you're doing.
Solid.
What's that?
Charlotte, not Chapel Hill.
Yeah. Oh, it's a Chapel. Oh, I apologize. Solid. UNC Charlotte.
And I think
yes.
Bala is at NIST, but don't.
Oh, he is?
Yeah.
Okay. All right. This is a great book. If you get I highly recommend getting your hands on a copy. It's written in MATLAB, but actually a lot of the MATLAB code translates very easily to R. In fact, that's kind of what I've done for this little screenshot here. When they start talking about Fourier transforms in this book, you'll see exactly this picture. And this is my code to do it, and it looks very much like the code that's in here in MATLAB. So pretty much everything that they talk about in this book is easily reproducible in either MATLAB, they tell you literally how to do it, or in R. And that's kind of how I learned how to program. I reproduced a lot of people's examples, and eventually I started messing around with it, tweaking them a little bit, and learning how do I get things to change the way I want them to change. So I really like this book if you're into surface metrology, but you don't necessarily have a lot of experience with either something like MATLAB or R or whatever. They're really very gentle in here. So this is what RStudio looks like when it's fired up. If you ever do install this program, install R first. You'll probably never have to actually look at the R executable again, because as soon as R is installed, RStudio knows how to find the executable, and you just work with RStudio at that point. If you just install RStudio and try to use R, they haven't. Last time I checked, it doesn't come with its own distribution of R. Yeah, it has to find the R executable on your computer someplace. So this has to go in second. But once it's in, you have a couple of different windows that you're looking at, and this is how I have things set up. You can drag these windows around and move them wherever you want. This is kind of how I have things, which is basically the default setting. I just changed the background to blue instead of white. You have your scripting window where you type in your commands, and they're just text files, so they can be saved in perpetuity. You could either run blocks of code at once, or you can run them line by line, which is something that, as far as I know, you cannot do in MATLAB. If you run a script in MATLAB, you run the whole script, and that's it. You can't just do it line by line, whereas with this program, you can do it line by line.
You can do line by line from the debug.
Okay. Window. Is there a debug window?
Yeah.
Okay.
Yeah.
All right. So you have your scripting window. Then you have your console window, where basically you take commands up here and you send them to your console window and it executes them at the command line. Or you could literally just type commands in at the command line. I rarely do that unless I'm experimenting with new something weirds, because whatever you type at the command line isn't saved for you. You can scroll, like in Unix, you can use the up and down arrow keys to scroll back through your history. But again, if you're writing something new or you're doing an analysis and you're really not sure what you're doing, I always type it in up in my script editor. So I have my script save, and then I execute stuff down at the command line, either in blocks of code or line by line. Your plots, and when I was talking about your plots coming out a little small, this is what I was talking about. They're usually like over off in the corner over here. You can make this window as big as you want, but then it will take away from whatever you're typing over here. The nice thing about this, and if RStudio didn't have this feature, I probably wouldn't use it. You could take this picture and you can click one of these buttons up here. It'll dislodge the plot and it'll make it big, so you can stretch it out and look at it however you want it. And then also another nice thing about this is the help is pretty decent. One of the nice things about R is if you want to post a new R add-on to the CRAN website, you have to write help files for it. Otherwise, it does not allow you to compile the program at all. So people have been forced to writing help files, and if you have to do it, you might as well do a decent job. So people have written pretty descriptive help files for it, and I'll talk about getting that help information up if you want to get a little bit of information about the functions that you happen to be using, and they come out over here. Also, again, because this is small, one of the nice things about it is you can dislodge this and it'll make it a big HTML, readable, beautiful. Actually, it doesn't look like HTML. It is in HTML, so it'll open up in your browser, but it is a human readable form, and you can click on things. It's dynamically linked. The only thing that I have seen that is better is I used to use Mathematica a lot. The Mathematica help. Has anybody ever used Mathematica? Well, I like Mathematica a lot. You guys are looking at me like, oh, that program. I like the help a lot in Mathematica because it has tons of examples in it that you can run and see how things work. That's the only one that I've seen that's better than this. But this does have dynamic links in it. You can click on it and go to other commands that are related to the command that you're looking at in that help file and da-da-da-da-da. So that's kind of what things look like, although when you fire it up for the first time, the backgrounds look white, not blue. I like blue, so I did that. Okay, let's talk a little bit about, once we have R installed, once we have RStudio installed, how do we start to use it? And there's a couple, like one of the hard things with any kind of program that I always felt is getting started. It's usually a big learning curve. And I learned on C first, which is really steep. This does not have to be that steep, and so let me show you some of the pointers to get started relatively quickly so you don't get absolutely frustrated and just throw your laptop out a window. So with R, if you want to get help on a particular command, let's say plot, you type command question mark and then the command name. So for example, if you wanted help on the plot command, type question mark plot, and either you send it to the command line or you just type that right in at the command line. The help file will come right up. And it looks like the help file that you just saw on the previous page. It's nicely formatted HTML. If you don't know what the name of a command is that you want to use, but you know a general concept, you could do one of two things. You can do what I usually do is I type R and then kind of what I want to do. When we first started learning about wavelets, and I wanted to know what wavelet capabilities were in R, I would type R. At Google, I would type R and wavelets, and I just started doing a lot of research myself. And in fact, a lot of things come up pretty quickly. You can quickly sort out there's not a lot of garbage that comes up, and you can quickly find these nerds that use this stuff love to tell what they love and what they don't love about these different packages. And you can come up with some of the packages or commands that might be of help to you. Then once you know specific command names, you can use the question mark syntax over here. You can also use question marks and then some keywords, and R might be able to pull up some help for you. I rarely, if ever, use this, so I usually just Google what I'm interested in, and enough information comes up that I can kind of find my way around the help files. Input. How do I get actual data into the program? So, because this is a data analysis program, besides it being a matrix engine, it's a data analysis program. How do I get data into the program? There are two major commands to do that. If you could literally type it in if you wanted to. I have rarely met anybody who will type in a spreadsheet into this program. You can, and what I usually do, especially if I have data saved in a spreadsheet, is I save it as a CSV file. Excel, no problem, saves stuff in CSV format. Save it as a CSV file, and you can use one of two functions in order to import that CSV file into R. The major one is read.csv. If you want help about it, you put a little question mark over here, and I'll give you some of the syntax for that. And I'll show you literally down here what it looks like in one of my programs. You could also use a lot of people like to use the read table function as well. This should work on a CSV file if you say, okay, and the record separators are not tabs, but commas. And this function gives you the ability to do that. R can literally read an Excel file. We have tried that, and it runs a little slower. And you need an extra R package in order to do it. So if you want to save yourself a little bit of a headache in installing an R package, and it's going to run slower anyway, just save your Excel files as CSV files and pull them right in. Especially if the files are not that big, you might as well just do it this way. One thing to watch out for, if you have an Excel file with a lot of tabs on it, so in other words, you have a bunch of different data in different tabs, then this will screw up. It only grabs the first tab and ignores everything else. There probably is a way to get it to recognize other tabs, and maybe that added Excel functionality that is available in R can handle it. I have never played with it myself, though. So usually if I have a spreadsheet that I want to pull in, I just make sure it has the one tab in it with any data that I'm interested in. I save it as a CSV file and I pull it in. So that's what I have to say about that. In that script that you have on your thumb drive file thing here, if you want to pull in the parameters file, so I call the parameters parameter_data.csv, this is what the syntax will look like. It looks complicated, but it's actually not that bad. Basically, you have to tell it where the file is. In other words, you need the path and the file name. So I'm using read CSV. Any text string in this program is put in quotes. Not one quote, not one asterisk, not a parenthesis, but double quotes like that. So this is a string. This will be lit up in a particular color for you in RStudio. I think it comes out green or something like that. This is the path to my file over here. And one of the other things that's handy for this particular command is whether or not you have a header. In other words, what I like to do and what I tell all my graduate students to do is don't just give me a spreadsheet full of a bunch of numbers. I don't know what that means. Label it a little bit. At the very least, tell me what each column is supposed to be. That R understands is the header. So if you do have headers on your columns, in other words, the first element of every column is actually some kind of a descriptor, you flip the switch, header equals true. If you don't have headers, you say header equals false. By default, if you don't put anything in, it assumes that you have no headers. So if you do have a bunch of text on the first line, it'll read it in as data, which you usually don't want. So this is basically the syntax I always use. If I have a new file, I don't really have to change anything other than the path. There is a way to use a GUI to get the path, and I'll talk about that when we open up the scripts. But usually I just because I don't move my file when I'm doing a research project. Usually my files stay in the same place all the time. And if I have to go through a GUI every single time I want to open up a file, it's a pain. So I usually just type my path in once, and then every time I open up the script, I just execute the same line of code. And if you want a different file, if you have a different path or a different file that you want to look at, you just change the path and the name, and that's it. So Excel always saves in CSV format, and no matter what I've used all the operating systems, no matter what operating system you have, you always can save as a CSV file. And the other nice thing about CSV files is just text files. So you can open them up in any text editor as well and look at them, and it's not a bunch of gibberish binary. How am I doing for time here? 2:30. Let's go for another 15 minutes, half hour, and then we'll have a break, and then we'll pick up the second half. Okay? That sound okay for people? Great. So, again, because this is a tutorial, and because I get the strong impression, again, I'm not a trained engineer. I'm a mathematician. But I get the strong impression that the Digital Surf company has really made a profound mark on surface metrology, and that a lot of people use mountains. One of the things that I really like about the mountains is that they have published the file format. So you know exactly what the headers are and where the data is and da 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 da. So I think it would actually make a good standard if you wanted to have a binary standard for surface data. I don't know. I'll put in my 2 cents at the ASME meeting, but this is a file. This is what we use as a standard. So no matter what scope we're using, we always, if we want to look at anybody else's data, I always tell them, please open it up in Mountains and save it in a .sur format, so I know exactly what I'm looking at. So you can, with R, we have written a little add-on, which the code is on here. So you can just type the path to the file. As long as it was saved in Mountains, it will open up the file and give you all the header information. In order to do that, you could do one of 2 things. If you don't know what the path to your file is, you can use the file choose command. So this is an R command that I did not write. This is written by R people. It brings up one of these GUIs, and you can go through all the GUI and find your file. What it does is it returns the string, which it represents the path to the file. And you can take that string and you send it to the function that we did write, read digital surf file. I didn't know how to make it more obvious than that, but that file will open up a digital surf file and everything gets read out. It actually returns a list of lists. We'll talk about the format, so if you do use this, you know what you're looking at and how to get useful information out to you. But it takes a string, which is the path to the file, and it returns the file and all the header information if you want to use any of the header information. All of that information is getting dumped into the variable that I call surface.info. One thing to watch out for, and I wanted to go through some R code so you would get the nuances and differences between this and MATLAB, is the gets operator in R is backwards arrow, or what's that? Less than sign? Is that less than? Yeah, less than minus. It's backwards arrow is how I read it. Or actually what I always say is gets. Equals works as well. If you want to say 2 things are equal, that's the same as any other programming language, 2 equal signs. But you could use equals here. The convention has always been backwards arrow, so that's what I use. A lot of people, R codes stick to that. And I think it's because R actually comes from, R was originally developed from another program called S, which was developed at Bell Labs. S for statistics. The reason why it ended up being R.
Like going backwards, should we go from S to T?
Well, the reason why it ended up being R is because the 2 professors from New Zealand who developed an open source version of S. There was Ross was one of their names, and then the other guy was R too. So the major developers originally were their last names were R, so they picked R. It is an open source implementation of a program that was originally developed in Bell Labs for Unix called S for Statistics. I can't remember the names of the people at Chamberlain or something like that originally developed it. A lot of Unix utilities were developed at Bell Labs in the 80s. So this was one of them. And it has since been re-implemented as this open source and become kind of the standard way of implementing new statistical techniques. And I believe the original implementation of S, instead of using equals, it used backwards arrow. Either work. I always because everybody else uses it, that's what I stick to as well. And MATLAB won't know what that is, so MATLAB will say you're making some kind of crazy error. Right? So that's one of the annoying things to MATLAB users is some of the slight nuance syntax changes. But if you have enough gumption to get around that, there's only a couple of little things. If you can use MATLAB, you can use this program as well. And the only reason why I'm saying a lot about this and how wonderful R is it's a tutorial for R, right? I think MATLAB's great too. If you want to stick to that, great. Oh yeah, we do have some rudimentary function. Most of the time when we visualize surfaces, which is really, really important to do, because we were lucky enough to have funding to purchase a copy of Mountains, usually we do our visualization in Mountains, or as much as possible, we also do it in ImageJ because we have this little add-on to ImageJ. We have just recently started to implement some rudimentary things in R to visualize it. The problem, though, is that because I have a couple of million points that make up each surface, R is a little slow with it. And I have to decimate the surface in order to actually get it to come up within a reasonable amount of time. In other words, I throw away a bunch of points so I can visualize it. And it pixelates things a lot, and I don't like that. But you can do that. So this was produced with, I think it's in that little bit of code that I gave you. in one of those files that you can actually visualize it within R2. It's basically showing you a matrix, just a color-coded matrix, which represents the surface. If you have anything else that you can use, I recommend it. This program is mostly for number crunching, not big matrix visualizations. Mountains and MATLAB do a much better job at visualizing things than this program will at this point.
Is the neat digital surf file an add-on file that's not part of the native package?
No, I wrote it. And if you put this on your computer, you have it now.
It's somewhere in there.
Yeah, I'll show you where it is. We're going to run we're going to run all the. I have 3 major scripts I wrote for you. If this was a really interactive tutorial, we would run them all together. However, I have 1 day, and on top of that, we'd need to make sure everybody got everything right. We need a few, but I will run everything for you to see what it is capable of doing. We have more, so if you are interested in collaborating with us, great. But you have at least the rudimentary tools to get started with pulling surface info into this program and playing with it. If you want this also in MATLAB, Java, C, what else did we write it in? In Python, I have exactly the same routine written in those languages as well. And I stopped there because I was getting nuts. Okay, so at this point, I want you to at least know there's this program called R. And if you want to make things look pretty, you can use R Studio. It'll color code things very nicely for you. And it is a seamless IDE for R. I also want you to know how you get help with a command and how to pull in basically a CSV file into R. If you kind of have gotten the message that you can do these things in R, great. And you have enough information on here to attempt to get started. Don't be surprised at all if you fail the first time or it doesn't work right the first time. One of the problems that you'll have with the code that's on here is a couple of places I had to hardwire my path. So wherever I have files located on, and it's only a couple, but wherever I have files located on my computer, I have the path typed in there. If you get an error and you see the name Petraco anywhere, that's probably what's causing the error. You have to change the path to what's on your computer. We'll talk about this a little bit. After the break, I'll pull up all the scripts and we'll see where you have to change things. But don't get frustrated with the program. You're probably going to get frustrated, believe me. But with a little diligence, I have found it to be extremely useful in our research. So you know how to, in principle, pull data into the program. And one of the things that I just gave you now is you can open up digital surf files with it, thanks to the wonderful people at Digital Surf who published the format. If you do that, it is a good thing to know what my little program spits out at you, so you know kind of how to slice and dice it. And it spits out 2 things. Did you remember on the previous slide how I directed the output to a variable I called surface.info? I could have called it anything. I could have called it Nick Petraco if I wanted. I usually will try to name my variable something meaningful to me such that when I open this script up 2 or 3 years from now, I kind of know what I was doing with it. So you can call it anything. I happen to call it surface info. Okay. Within this variable that I named surface info, I have more information. I have information. Surface info itself is a R list, which is just a collection of information. And it's a list and not a vector because all those components in the list can be different lengths. It's like a ragged array in C. So surface info is a list which contains another list, and that's actually the header info. All of the numbers that tell you something physical about the surface, like how far apart the points are in space, what units you measured, maybe even measurement times, and different kinds of things that are stored in the digital surf header. And then it also consists of the second part of that surface info list is a matrix of z heights. Now, with our particular microscope, you guys save it as 16-bit numbers. So each surface height is actually a 16-bit number, which you multiply by a factor and you get a physical height. This function, the function that I wrote in R, does that for you. It looks at the header information and multiplies the integers by whatever it has to multiply them by, and you get surface heights out. So the numbers that come out of here are not 16-bit anymore. They're actual 64-bit numbers that come out at you, and they get spit out at you. You could look at any of this stuff, although be a little careful about trying to just print that out or trying to just visualize it, because it is a lot of information. And I have choked R. In fact, I've choked Java and C trying to spit things out because I didn't have particularly efficient visualization routine. So there is a significant amount of information in here when you try to look at it in 64-bit value. If you want, you can tweak the routine to just look at the 16-bit integers and then do whatever you want to them. I like to look at things physically, and also I figured that a lot of people are just getting started with the program, so instead of spitting out a bunch of meaningless information at you, what you measure should be what you see in this matrix here. If you want to see what's in surface info, you use the names command in R. So what I have tried to do is, with that little program, is in that list, I tried to put little text descriptors on what the elements are of that list. So if you say name surface info, it'll tell you what the tags of the other two things in there are. One I called surface info, which is the header information from digital surf. And the other one is the actual physical surface itself, converted into doubles, physical height format. Now, that surface info is a list. It's a list of lists. In order to look at the first element of that list, which is also a list, that's the header information. This is how you access different pigeonholes in that list. I'm not sure what you do in MATLAB, but if you're looking at a list in R, you use a double bracket notation. So to get the first element of this list, I do this. And in fact, I don't want to look at all that information because it's just going to be a lot of numbers. I want to look at what I named each of the pigeonholes in that, each of the cubby holes in that list. And if you do names this, all the names will get spit out for you. And what we tried to do is stick closely to whatever's in the digital surf documentation. I didn't go bananas writing exactly what they had in there. If you look at the documentation, the help file, they have a lot of good information in there. But basically, whatever they called that particular element of the header, that's what I called it too. So don't complain that this is called code. That's what they called it. But also other things, version number, and then the really important piece of information, the z increment. In other words, this is the number that I have to multiply those 16-bit values by in order to turn them into physical z heights. So all of that's in there. And you could look at it all either in name format or number format. So this is how you get the names out. The other really handy R command to have around is, let's say you do want to do some fancy new technique and you don't want to implement it yourself. And there's some R package out there that'll do it. How do you install it into your program framework? It's really simple. It does not take any kind of computing prowess whatsoever. You do have to have an internet connection, though. You have to be connected to the internet somehow. And hopefully, I've taught this at a medical school before, or a version of this talk at a medical school. And it's an absolute nightmare dealing with medical school networks because everything's locked down. If you're not on a lockdown network, you just type install.packages, so it's plural. That's something that my students always trip up on because apparently I talk fast and they don't hear the S at the end. It's an install packages. Quotes, open parenthesis, open quotes, whatever package name that you want, and that's usually what I'll find from Google. Close quotes, and it will go out and we'll find the package for you and install it. You might just have to tell it, which mirror do you want. So it may come up with a choice of, oh, where do you want to download this from? And you type a number. It'll say like someplace in Pennsylvania. And you type the number for Pennsylvania, which is probably Carnegie Mellon, because the big statistics program is, so they have a mirror. And it will go out, grab the package for you, download, install it. Any C code that's in there will compile for you. Usually it doesn't need to be compiled because whatever the package is has compile code in it for you. But it will do whatever you have to, and that's all you have to type. And it's installed, ready to use. Let's see what do I have on the next slide. Well, you guys think you could go a little longer, or you want to take a break at this point? I'm kind of throwing a lot at you at once.
We're supposed to take a break at 2:45.
Oh, we're supposed to take a break at 2:45? All right, let me finish this slide, then we'll take a break, okay? One of the things that you work with a lot in R or MATLAB or any kind of scientific computing is matrices. So this is a notation in R to deal with matrices. It's a little different than in MATLAB if that's what you're used to. So let me tell you how to do it. Let's say you have a matrix or a table of numbers, a two-dimensional matrix. You can go as high a dimension as you want, but most of the time I've worked with just two-dimensional matrices. I think that's what most people in engineering do. So if you have a two-dimensional matrix, how do I get, let's say, columns out, and how do I get rows out, or how do I access particular elements? Because usually that's what you're interested in. This is how you do it in R. Let's say I have a matrix called X. If I want just a column on X, I use this notation. Whatever I call the matrix, here I called it X. Square brackets, all rows, column 1. If there's a blank there, that means everything. Grab everything. So this means grab all possible rows, but only column 1. That grabs column 1 for you. If you want everything in a row, you say X, grab row. Here I just picked 3. Nothing next to the comma. That means grab everything, all columns. So grab row 3, all columns. This means grab all rows, column 1. Grabs a row, grabs a column. If you want an element, what if you wanted element 3-1? What do you think you would type? 3-1, right? That's it. So that's how you access a particular element of the matrix. These are really handy. I use them all the time when I'm slicing and dicing my data. Other handy matrix functions to use in this particular program are dim. What do you think that tells you?
Size.
Dimension. Yeah, size of the matrix. In MATLAB, it's size. In R, it's dim. This gives you the number of rows. This gives you the number of columns. R-bind and C-bind I use a lot. R-bind says if you have a bunch of vectors and you want to put them all into, and they're all row vectors, and you want to put them all into one giant matrix, that binds, send it all the vectors you want, it binds them up into a matrix. What do you think C-bind does? If you want them to be interpreted as column vectors, it puts them all into, it sandwiches a bunch of columns together for you. One thing to watch out for these is it's expecting as input all the vectors of the same length. If they aren't, it still may spit out results for you. It just might be gibberish. So just be careful when you send these guys vectors. In principle, they are all supposed to be the same length. It tries to do tricks to smooth things over, but that has never been what I wanted it to do. So every single time it did try to do something intelligent for me, it gave me garbage. So just watch out with these guys, but they are really, really handy. In other words, I want a bunch of rows and a bunch of columns in my matrix, but not everything. I'll slice and dice it with these guys a lot. So these are very, very handy to have around. Okay, last thing before we take a break. One of the really great things about scientific programming is writing little functions for yourself, because not every, some smart guy cannot interpret or cannot hope to know everything that the user is always going to want to do. So you're going to probably, especially if you like to do things nuts and bolts and by yourself, and you're not a WYSIWYG person, you're going to want to write your own functions. How do you do that in R? This is a notation. It's kind of similar to MATLAB. It looks a little bit different, but it accomplishes the same thing. You give the function a name. I just picked func.name here. Dot doesn't do anything. It's just interpreted as another character in R. So don't worry about the fact that I call anything dot in R. I think in MATLAB it gives you a hard time. I don't know. Anybody use MATLAB?
It's structures.
There's a data structure in MATLAB, and if you declare something to be a structure, dot is the separator
the separator
for structures.
I'm glad I asked, because in R, it's $. So instead of using dot, use dollar. Yeah, don't name anything with $signs in R, but dots are fine. It's probably the opposite in MATLAB.
Underscores safe?
Yes, underscores. Yes, underscores are safe. Yes,
underscores are also safe in MATLAB.
Mathematica, they're really not. They're really bad. Don't use underscores for anything other than be careful in Mathematica with underscores are fine here. I almost always use dot because it's just easier to type. Yeah, underscore's okay.
Yeah, you have to hit 2 buttons to get an underscore.
Yeah.
Single button gets you.
Yeah. This is minus sign though. This is not underscore, even though it looks like minus sign. It's underscore. So this is. Pick a name for your function. Gets, use the keyword function. So don't actually name anything function. It'll work if you try, but don't try to name anything function in
At the
R.
end of that session.
Yeah. Well, it'll probably work, but it's really not a good idea. You're going to have ugly masking going on. You send the function, whatever you happen to call it, whatever list of arguments you want, it does something, and you put it in between curly brackets. It doesn't matter. Spacing does not matter. I just happen to space things like you space in C. You put them inside curly brackets, your code for the function, and then your function doesn't, it depends. You can get real fancy and you can start playing around with global and local variables, but usually I just try to keep it simple and return something. So everything within my function is local to that instance of the function. And then when it does something, I calculate a value, I return that value.
That's the default.
And that's the default, and that's how I like to do it, keep it simple and not go bananas with things. I'm a real, Street Fighter type of programmer. I just make it work and make it work simple. So that's the simplest thing I know how to do. And that's kind of what they recommend to do in the R documentation. Then once you have defined your function and you've loaded it into memory by executing these statements, it doesn't do anything, it just loads it into memory. Now, if you want to use your function, you call your function name, and then you stick in the values that you want. It will spit something out at you, whatever the output happens to be. So those are the most useful things I know of to tell you about in order to get started using this program. How to get information into it, how to get help about different kinds of functions for it, and how to write your own user-defined functions. Once you know those three things, you can really get started on your own doing whatever it is that you want to do. Let's take a break, and then I put if you're like me, you like to actually see hard-coded examples. So the next slide, I'll leave it up here if you want to take a look at it during the break. This is just a hard-coded example. I figured this is a Surface Metrology conference, so I'll write a little function for a Surface Metrology parameter. So this is a code that I have for RQ, a little function that I wrote. And then here is the syntax for once you have a surface, load that surface in and do calculate an RQ on one of the profiles of that surface. So if you want to take
digital RQ as opposed to an analog.
Yes, yes. You can do digital. You can integrate, and I think it always boils down to some kind of numerical integration.
Sure,
but
it's going to be either trapezoid or one of those methods.
Yeah, you can numerically integrate with like Simpson's rule or something like that with this. But also, in fact, I'm teaching physical chemistry and we're doing quantum mechanics this semester. So one of the things I want the kids to do is write their own little R scripts to calculate wave functions instead of doing it by hand, which is annoying and nobody does it like that anymore. And we have to integrate things. So actually, we do have experience. What we're doing right now is we take a bunch of points, which represent the wave function values, and we spline it together. Then we send that to the integrate function. But I think, ultimately, the integrate function is doing something like Simpson's rule. Yeah. But yeah, just be careful. If you want to numerically integrate things, I am not an expert at all in this program as to how accurate things are and what good techniques are, so look it up. I don't really know how well it does work. I haven't had to do it a lot yet. Let's take a break. On break, I'll leave this up for 5 minutes and I'll pull up the website and I'll also pull up the R website so you can kind of see where you need to go to get things.
We're back at 3:15.
Yeah, let's do, 3:15. 3:15, that sound good?
3:15 is the official schedule.
Oh, is that it? Okay, great.
Works out.